Okay, so what we want to do today is, for the first part of the class, finish up our remaining few points regarding deterministic dynamic programming. Hopefully you guys have had a chance to review those theorems and you kind of understand the concepts. We are then going to immediately move into the next topic of this course, which probably is the most important kind of workhorse model that we'll discuss, is the optimal growth model, where we will use these dynamic programming theorems in order to characterize and analyze the solution to that particular model, okay? And that will probably take, I'm guessing, at least 3 full classes to get through. And then we will move into an alternative treatment of the optimal growth model, where we don't look at it from the perspective of a benevolent central planner, but rather we look at it from a decentralized competitive environment, the so-called neoclassical growth model. You might not be, this might not be so surprising that the equilibrium and the allocations that come out of those 2 models are going to be the same, because there are no frictions or distortions which cause the competitive outcomes not also to be Pareto optimal, right? This is not what we saw in the OLG model. In the OLG model, we saw that we could very easily have overaccumulation of capital, right? So the competitive outcomes don't necessarily correspond to the socially optimal ones. The growth model, the infinite horizon growth model that we're going to talk about, the neoclassical growth model, is an example of a model where there is no wedge between those 2, okay? And that will carry us then through your next exam several weeks down the road, okay? All right, so I think this is where we left off in our discussion of dynamic programming. We basically went through all of the assumptions necessary to establish theorems 1 through 6, which show, among other things, that the value functions that come out of the sequence problem and the Bellman equation are equivalent, that the principle of optimality holds, that the value function can be broken into 2 parts, the current return plus the discounted continuation return, that the value function is unique and continuous and bounded, that it's strictly concave, and therefore a unique optimal policy function can be found, which implements the optimal value function. And we also established some results concerning the monotonicity of the value function, its differentiability, where we apply the envelope theorem to differentiate the value function. So all of that today culminates in this discussion of theorem 7, which I'll just kind of read, and then we will discuss an important component of it a bit more informally, but not go through a formal proof of it, okay? Let capital X on as a subset of k-dimensional Euclidean space, and then assume that assumptions 1 through 5 hold. Okay, if we've identified a sequence, let's call it X star, such that xt plus 1 is in the interior of G, the constraint set, for all t, and that sequence of controls is optimal for the sequence problem as well as the functional equation for any given initial x, if and only if it satisfies 2 criteria. This is what kind of the dynamic programming theorems culminate in, okay? If we've identified what we think of as an optimal plan to this infinite horizon problem, then it has to satisfy 2 conditions. One is what we've called the intertemporal Euler equations, right? Which says that the derivative of the payoff function with respect to the second argument, that is the control, xt plus 1, plus the discounted value of the derivative of the payoff function with respect to the state, scrolled 1 period ahead. So u xt plus 1 star xt plus 2 star has to be equal to 0. This is the intertemporal Euler equation, or the set of Euler equations if x is k dimensional, right? It basically shows us the slope of the x profile over time. That is not the only optimality condition though, right? We require this other very important condition that must hold along an optimal policy, and that is the transversality condition, which says that the limit as t approaches infinity of the discounted value of the, I guess you can interpret this as the marginal value of the state. So the derivative of the payoff function with respect to the state, that is the first argument, times the state has to be equal to 0. And these equations hold along a candidate optimal sequence of x stars. So this theorem 7 states that the transversality condition is both necessary and sufficient for an interior optimal plan, as long as it also satisfies the Euler equations as well. Okay, the Euler equations are obviously also going to be necessary for an interior solution. Now, what is the point of this? When you guys are utilizing dynamic programming to try to characterize the solution to an infinite horizon sequence problem, most often the only thing you need to derive to characterize that solution are the set of intertemporal Euler equations, as well as a statement of the transversality condition. The optimal policy function, as well as the value function, should satisfy these conditions. That's the task here at hand. I present you with a sequence problem, a dynamic infinite horizon sequence problem. Step 1 is to rewrite that problem in terms of a Bellman equation, that is the recursive form. From that recursive form, the functional equation, you derive the Euler equations, which fall from what? The first order conditions, as well as the envelope conditions. You combine them to get this intertemporal Euler equation. That, in conjunction with the transversality condition, is enough to fully characterize the solution to one of these infinite horizon sequence problems. Okay, we're going to apply this theorem to the optimal growth model a little bit later today, or we're going to start doing that a little bit later today. Okay, so the first thing that I want to accomplish today is to discuss in a little bit more detail this equation, the transversality condition. What is it saying exactly? Where the heck does it come from? Your textbook author has a formal proof, if I'm remembering this right, of why the transversality condition has to hold along an optimal plan. You're more than welcome to go and try to work through that proof. I'm not going to do it in class here. What I'm going to do is I'm going to kind of prove this informally or heuristically by motivating the transversality condition from a finite horizon sequence problem. So instead of imagining that time goes on forever, let's say that the state of the world ends at some date cap t, where cap t is a long time from now. If we take the limit as t gets to a really big number, we can approach something that looks like an infinite horizon problem. And hopefully that'll provide you with some intuition about where this transversality condition is coming from. You guys may not see this yet, but the transversality condition is a really important condition for establishing the existence, uniqueness, and stability of the equilibrium path in the neoclassical growth model. We have to appeal to the transversality condition in order to establish the stability and existence of that path to the steady state. Okay. Now, what we're going to talk about in a few weeks is how the transversality condition is also very much related to a different concept that has much more economic intuition, and that is the family's or the representative agent's lifetime budget constraint, which says that the present value of your lifetime consumption cannot exceed the present value of your lifetime resources, that is your wage income as well as the initial level of assets that you have at the start of time. That is an intertemporal budget constraint that is very much connected to this transversality condition. So you won't see that yet, but it's going to come into play to be really important in the coming weeks. Okay, to try to motivate this a little bit, let's go back to the sequence problem for a second. And let's also consider a simplified version where xt, the control, is just on the positive real. So it's just a scalar instead of some k-dimensional vector. And we're going to say that time is finite. So cap t is the end of time, less than infinity. So what the planner is going to attempt to do here in this problem is to maximize over a sequence of x's from date 0 to cap t instead, the sum from t is equal to 0 to infinity of beta to the t, u xt, xt plus 1, subject to, let's say, just a non-negativity constraint on the x's, and some given initial value of x. Okay, so here is a statement of the sequence problem, and this was a generic sequence problem for the case in which x is a scalar, a positive scalar. Okay, let me denote u x cap t plus 1 as this is kind of last period utility. Your utility every period depends on xt as well as xt plus 1. So in the final period of your life, your utility depends on the state of the world at cap t, but also what the state is going to look like, I guess, in the afterlife, right, at date cap t plus 1. Okay, so we have a finite dimensional optimization problem. So we can apply the Kuhn-Tucker theorem to solve this constrained optimization problem, right? I'm going to assume that an interior solution exists, right? That is, xt star is greater than 0 for all t, from 0 to cap t, all right? So I'm going to do this just to make a simplification. When you apply the Kuhn-Tucker theorem, hopefully you guys learned this in math camp, you have to, the first order conditions are written in complementary slackness form, right? You have to account for the fact that there might be corner solutions. I'm going to just assume that there are only interior solutions here. So we can write the first order conditions in the standard way, okay? What is the first order condition with respect to x1 then? Remember, x0 is given. The planner's not choosing x0. She's choosing x1 through x cap t. What's the derivative of the objective function with respect to x1? Well, x1 appears twice in this sum, right? Where there's a ux1, x2, but also where there's a ux0, x1, right? So it would be the partial then of u of x0, x1 with respect to the second argument, right? And that's a beta to the 0, so there's no beta there, plus beta to the 1 times the partial of u x1, x2 with respect to the first argument. That has to be equal to 0. You guys see how I did that? The derivative of this lifetime objective with respect to x1, well, x1 appears in two terms. It appears in ux0, x1, and it appears in ux1, x2. What is the derivative with respect to x2? Well, that would be what? That would be beta times the partial of u x1, x2 with respect to the second argument, plus beta squared times the partial of u x2, x3 with respect to the first argument. That is equal to 0. And something cancels, right? One of the betas cancel. So this first order condition and this one start to look similar, right? Now, what if I do the first order conditions all the way to x cap t? So there's cap t of them. Well, you would have a what? A beta to the cap t minus 1, partial of u x cap t minus 1 x cap t with respect to the second argument, plus beta to the cap t partial of u x cap t plus 1 with respect to the first argument is equal to 0. And in this case, beta to the t minus 1 would actually cancel. And what are you going to be left with? Sorry. If I had eyes in the back of my head, I could see that better, but I don't. The system of first order conditions takes a general form, right? It's the partial of u x t star x t plus 1 star with respect to the second argument, plus beta times the partial of u x t plus 1 star x t plus 2 star with respect to the first argument is equal to 0 for all t between 0, 1, 2, all the way up to cap t minus 1. And here, x 0 star is just equal to the initial value of x. This equation is just the Euler equation that we derived earlier, right? The marginal utility of the control plus the discounted marginal utility of the state scrolled forward one period is equal to 0. Okay, now let's take stock of what we have here. How many first order conditions do we have? How many equations do we have here? We have t equations, right? How many unknown variables do we have? Well, we're trying to solve for what? x1 star, x2 star, all the way to x cap t star, right? So we have t unknowns. In principle, you can solve for those t unknowns using those t equations. It's a fully identified system, right? What's the only problem with trying to do that, aside from the fact that t may be a really big number? In order to solve for x cap t, for example, from the last first order equation, what do we have to know? You actually have to know what the value of x cap t plus 1 is, which we don't know. If we knew what x cap t plus 1 was, we could plug that in here, and then we would have a fully identified system, right? So really, there's t plus 1 unknowns to be correct, right? There's x1 through x cap t plus 1. So we're missing an equation that would identify all of the variables we're looking for. That is x1 through x cap t plus 1. What do you think that last equation looks like? If these first order conditions look a lot like the Euler equation, that last equation, which pins down xt plus 1, it's probably going to look sort of like a transversality condition. That was the point of doing this in finite horizon form, is to show you kind of where it comes from. Okay? Let's pretend for a moment that xt plus 1 was determined optimally. Okay? If xt plus 1 was determined optimally by the planner here, then what would the first order condition look like? Well, x cap t plus 1 only appears in one utility function, the very last one. It doesn't depend on two utility functions like the rest of the x's do. So it would be beta, so the derivative with the first order condition with respect to x t plus 1 would look like the following. Beta to the cap t plus 1 times the partial of u x t x cap t plus 1 with respect to the second argument. Now, for this condition, however, I'm going to have to write this in terms of complementary slackness form because it's not clear to me yet that xt plus 1 should be an interior solution. If you die at the end of period t, it's not clear to me at all if there's any value to having some positive value of xt plus 1. So there could very well be a corner solution here, right? So the complementary slackness form of this first order condition would be the partial of u xt xt plus 1 with respect to the second argument times beta to the t plus 1 times xt plus 1 is equal to 0, with x cap t plus 1 star being greater than or equal to 0. That's what the first order condition looks like in complementary slackness form. It accounts for the possibility that xt plus 1, the optimal value of xt plus 1, may be 0. If it is, then this term here does not have to be equal to 0. However, if there is an interior solution, then this derivative here has to be equal to 0, right? So we write this in complementary slackness form to account for both possibilities. Okay, we can derive something that looks identical to the transversality condition heuristically. That is, if we use kind of informal arguments, by taking the limit of this expression as, let's say, cap t approaches infinity. Okay, so let's just take the limit then as cap t approaches infinity of the first order condition, beta to the cap t plus 1, partial of u xt xt plus 1 with respect to the second argument times x cap t plus 1 is equal to 0. That has to hold for all t, even as t approaches infinity. Now, as t gets really big, what would the Euler equation look like? So imagine instead of stopping time at the end of t, we stop time at some number way bigger than t. The first order condition with respect to cap t plus 1 would look like the following. Partial of u xt xt plus 1 with respect to the second argument plus beta partial of u xt plus 1 xt plus 2 with respect to the first argument is equal to 0. Let me use this Euler equation that would prevail again if time kind of went on longer to substitute this thing here out of my limit expression. What's the partial of u xt xt plus 1 with respect to the second argument equal to? It should just be equal to what? Negative beta times this one here, right? So this limit expression becomes the negative I have a mistake here that y'all didn't catch. Shame on you. This should be beta to the cap t, not beta to the cap t plus 1. So if I substitute this information back into my limit expression, I would get the negative of the limit as cap t goes to infinity of this time beta to the cap t plus 1, right? So it's beta to the cap t times a beta times the partial then of u evaluated at x cap t plus 1, x cap t plus 2 with respect to the first argument times x cap t plus 1 star is equal to 0. So all I'm doing there is I'm using this Euler equation and plugging it back into my limit expression. Now we can simplify this, right? The negative sign will cancel because the whole thing is equal to 0. And since we're taking t out to infinity, we can scroll all of these times back one period, and it doesn't affect the limit at all. So we can take this becomes the limit as t goes to infinity of beta to the cap t partial of u xt plus 1 with respect to the first argument times xt is equal to 0. Now, if I simply do a quick change of notation, if I change my cap t's to little t's, that doesn't matter. This becomes the limit as little t goes to infinity of beta to the little t. And let me just reinsert vector notation here. So I've done this using scalars, but this is basically just the gradient with respect to the first k arguments of u xt star xt plus 1 star inner product xt star is equal to 0. And what do you have? That is the transversality condition. In other words, one way of viewing what the transversality condition is would be to take a finite horizon problem and evaluate the first order condition in complementary slackness form of the last value of the state, and then shoot t off to infinity. And what that gives you is something that is identical to the transversality condition. It is a term, you can think of it then as a terminal, if this is the terminal value condition in a finite horizon problem, right? It's this complementary slackness form for the first order condition with respect to x t plus 1. The transversality condition is very much like a terminal value condition for an infinite horizon problem. And it actually does have a lot of economic intuition when we look at the neoclassical growth model, because this statement of the transversality condition, it turns out, is going to be equivalent to saying that the representative agent's lifetime budget constraint has to bind, meaning that agents will make sure that they consume a consumption trajectory over time that fully exhausts the present value of their lifetime resources. That is equivalent to a statement of the transversality condition, and is critical to a statement of optimality in these infinite horizon problems. Okay? Any questions about that? So, I guess the first part of this section is to make sure you understand what all of the notation means, right? Lifetime objectives, a constraint correspondence, states versus controls in the context of a sequence problem. How can that sequence problem be mapped into some other type of problem that is easier to work with? That is a functional equation or a Bellman equation. That's the first thing you do. Then, can we apply the theorems which establish equivalency between those two problems? That is the Bellman equation and the sequence problem. What assumptions do we need to show in order to make that equivalency? Once we've established that, we can then work with dynamic programming problems or characterize the solution to those problems with Theorem 7 by deriving the Euler equations and the transversality condition. Together, those two pieces of information fully characterize the solution to these types of models or types of economic problems. Any last questions about this?